All right, let's go ahead and get started. Welcome to CS 374, Algorithms and Models of Computation, otherwise known as Theory 1. Thank you for being guinea pigs. My name's Jeff. I'm the instructor. Abigail's one of the course staff. Are there any of the other course staff here? Yeah, there's a couple more in the back. You'll see them again in the discussion / lab sections either tomorrow or Friday. I haven't added them to the official course webpage yet because I'm still waiting for some paperwork to go through. But you can find everything that you ever wanted to know about this course on the web, and probably quite a bit more. But let me give you, the first summary in case anyone is the least bit confused about where you are. This course, right now it's a 498, but eventually the aim is to have it be a regular course called CS 374. This will replace both CS 373, Intro to Theory of Computing, and CS 473, Fundamental Algorithms, in the undergraduate computer science curriculum as the required theory course. It's also going to become the required algorithms course for the computer engineering curriculum, where currently there's a placeholder there called CS 473. But as soon as CS 374 is a real course, that will change. Okay, so this is eventually a course that is going to be required for 2 of the largest majors on campus, with an anticipated enrollment of 400 students per semester. That means 2 things. 1, we don't know what we're doing. This is we've had 373 and 473 as 2 separate courses for at least 30 years. Not always with those numbers, but always at least 2 separate courses. And so trying to fit stuff into a single 4-hour course requires some painful choices and some rather, unfortunately for you, painful learning process for how to teach a combined course in a cohesive way without absolutely, completely overwhelming you. We will try to be fair, but please remember that we don't know what we're doing. The second thing is, this is ultimately going to be a course that will be taken by 50% of the College of Engineering, which means everything we do, even though there are only 90 or so of you here, everything we do is going to be aimed at what happens when there are 400 of you. Which means some of the things we do may seem a little bit micromanagey. Like, we want you to submit written homework on printer paper rather than on notebook paper. Part of that is we're trying to figure out the logistical processes involved with teaching a class of 400 without experimenting on 400 people at a time. So the very first thing that I want to ask of you is, if something is going well or if something is going badly, please let us know. We're going to be using Piazza for class discussions. I have it set up so that you can sign up anonymously using a fake email address that you found in a dumpster. I won't know who you are. Even if you sign up with your Illinois address, you can post anonymously and I won't know who you are. Please feel free, either post publicly, send me a private message, slip a note under my door, talk to one of the course assistants, talk to one of the TAs, talk to a different professor in the department. But please, as the course goes, it's very, very important for you to let us know what works and what doesn't, so that we can remember that for, we can make changes this semester and we can pass on those lessons for next semester when we'll be over in ECE. There's lots of seats up front. I know that's scary, but I don't bite. Okay. The first thing you can see on the course webpage is there is a homework 0. It's due on Tuesday at noon. There are drop boxes over in 1404. Ultimately, there will be 3 of them, one labeled 1, one labeled 2, and one labeled 3, to throw the 3 problems in. You'll also notice, somewhat confusingly, there are 4 problems. Again, this is sort of it's a cute problem. I couldn't pass up the chance to ask it. We wouldn't do this with 400 students. Extra credit here means we will figure out the curve and then we will add the points. So, you know, this is stuff that you can only raise your grade if you attempt it. So, please try. Okay. Now, there it is. You can see, you know, submit your results on printer paper. There are a couple other policies in this course that are starting to leak their way into other courses you might have taken, but not all of them are going to be familiar. One is, I will only use this word once, hopefully, in the entire semester. Don't bullshit. If you don't know the answer, just say, I don't know. We'll give you 25% immediately, no questions asked. Any homework problem, any exam problem, Part B, subpart 2 to any exam problem. We won't do that, but you get the idea. The idea is, it's better, you're demonstrating more knowledge by saying, I don't know, than by writing a bunch of stuff hoping to get some mercy points when you don't know what you're doing. This is partly a pedagogical thing, and it's partly a purely practical thing. It's hard to read that nonsense. And so the graders and the TAs and I are just going to adopt the policy. If we see something that looks like nonsense, it's a question mark 0 and move on. Okay. So it's also really in the interest of speeding up the grading process. There are a few deadly sins. Some of these are long-standing things that we've been doing forever. Some of them are not. The one that has been a long-standing thing, and this will come up again and again over the course of the semester. When we ask you to write a proof, don't give examples and say and so on. When you ask you to describe an algorithm, don't give us the first 2 iterations and then say and so on. If there's supposed to be a loop, write it as a loop. If there's supposed to be induction, write it as induction. If it's supposed to be recursive, write it recursively. I should be able to plug in whatever number I want into, I want to know what happens in the 3,773rd iteration of something. I should be able to plug in the number 3773 somewhere and mechanically figure out what happens. Otherwise, it's not a proof, it's not an algorithm, it doesn't get any credit. Second, this one's new, based on our experience last semester with the first set of guinea pigs. Declare your variables. Every time you introduce a new symbol, tell us what it means in English. For example, let n be an arbitrary positive integer. I've told you exactly what the symbol n means. It's an integer, and moreover, you know nothing else about it. Right? Here is a function I'm going to call f, and here's what that function means in English, and then here's how you express that function recursively, and then here's how you write an algorithm to actually implement that recurrence. We want to know what you're trying to do before you do it. And we want to make sure you know what you're trying to do before you do it. So this is just like writing code in one of those hand-holdy type languages like C, where you have to declare all your types. Exactly the same, except in English. The last one is, thou shalt not use weak induction. Never. Absolutely never. In particular, thou shalt not write a proof that assumes something about n and proves something about n plus 1. Never. Absolutely never. Weak induction does not exist. You'll see examples of this tomorrow in section. If you use weak induction, there are only 2 options. Either you're perfect and you get a perfect score, or you don't and you get a 0. Don't tie n minus 2 hands behind your back. Use strong induction. Okay. There are a bunch of other micromanaging course policies explained on the website, how we're going to do grading, how we're going to hand stuff back, what our expectations are for what you write, but I'll just let you look at the course webpage for that. Okay. The only other thing that I want to mention about course policy before I go any further, and I have to apologize in advance for having to say this, but inevitably about 1% of any class has a problem with this in any given semester. So the short version is, don't pretend that you did something you didn't. Give credit and be generous about giving credit. So I don't care if you use Wikipedia. I don't care if you talk to each other. I don't care if you talk to other grad students. I don't care if you go to the library. I don't care if your mom is a theoretical computer scientist who has a Turing Award. If you talk to people and you get ideas that help when solving your homework problem, just say, I got help from mom. If you got help in office hours, just say, I got help in office hours. If you got help in some discussion at Granger with 25 students whose names you don't all know, just say, I got help at a Wednesday evening discussion thing at Granger. Okay? Just cite your sources. Beyond that, don't care what sources you use. Everything is fair game. The other thing is, write everything in your own words. So don't say, I got help from my mom and she said, and paste the email from your mom. Okay? I have probably a dozen times in the last 16 years gotten printouts of Wikipedia pages. When we ask you to solve problems, what we're really asking is for you to demonstrate your expertise. Demonstrate what you know and what you can do with the course material. Just photocopying or transcribing Wikipedia or my solutions from 2 years ago, which, by the way, I have. I have to say that, because every so often I get them. Typos and all, which is how we identify them. You're not demonstrating your expertise, which means you're robbing yourself of the opportunity to get feedback, which is the point of the homework. You're supposed to be getting feedback on how am I doing. And in particular, when we start going to group homeworks, this is crucial. And again, I have to say this because students have been burned by this in the past. When we start doing group homeworks, there'll be 3 people signing their names to the same homework. If one of you plagiarizes, well, all 3 of your names are at the top. You all get the same penalty. So this means, 1, choose your partners carefully, and 2, don't screw over other people. This is exactly the same thing that would happen if I wrote a paper with a grad student who plagiarized from some other paper or cooked data or something along those lines. This is one of the few things that can happen to me that would cost me my job. Right? If some of my students decided to just steal stuff or make stuff up and it came out, that's it for me. Doesn't matter whether I have tenure or not, I'm gone. Okay? So this is exactly the same standard that I'm expecting from you. All right? When things come up, if there's any question about where the line is, I'm not really sure. Does this, is this too close to what somebody else has said that it's likely to get me in trouble? Ask. Just ask us. If all else, when in doubt, just ask. If you're not sure whether somebody's given you enough to give them credit or not, the answer is yes, give them credit. Your grade does not depend in any way on who you thank, except that if you don't thank anyone, then it's clear that you should have. Okay? Penalties and stuff are described on the course webpage again, but these are pretty consistent with what other people do in other CS and CE classes. So I don't want to belabor this point. Are there any questions about course policy or administration or anything like that now before I actually go on to why you're here? Yes. Office hours start this week. So in particular, I have office hours tomorrow morning. Yeah. So there's a question of whether there will be sort of tutoring hours. So generally, the office hours are there for us first to be able to answer any administrative questions like this, or hey, you gave me a 0 on homework I think is worth 75% or more, or where's my midterm? Yes, that's happened once. I had made the mistake many, many years ago of leaving a box of graded midterms outside my office. The janitor was very helpful and threw them away for me. But it's also there to answer questions about the course material. If there are things that are unclear from lecture, if there are things that are unclear from discussion sections, that's where, those are the kinds of things we'll ask in office hours. If there are no other questions about that sort of stuff, then we'll take, questions about, this week's homework. If you need hints or suggestions or feedback on, hey, I think it's going to be, I think I should do it this way. Is that the right approach? I'm stuck on this point. Can you give me a hint to move forward? If you think you might need somewhat more focused or dedicated tutoring, this is something to bring up with the people, the course assistants. As I've told them, they have a minimal set of responsibilities, but if they want to take on additional responsibilities, I'm happy to pay them to do that. And tutoring might be one of the things they're willing to do. You might also talk to people in the ACM office in Siebel. ACM is full of incredibly smart people, some of whom have taken this class or equivalent classes. Often ACM or other organizations like Women in CS. I don't know as much about similar organizations over in ECE, but I imagine there's something like a student chapter of HKN that might also be willing to do some tutoring. Post on Piazza, posters up in Siebel saying help. People are really quite eager to help if you offer money. And I'm happy to help with that search to the extent that I can. Lectures are being recorded. This lecture is being recorded. All of the videos, they're collected on an automatic thing. Over time, I will pull links over to the schedule page. But yeah, every lecture will be recorded. I absolutely do not have any sort of attendance requirement, either in lecture or in lab. If you're more comfortable watching the video at double speed at 3 in the morning, if you're more happier watching the video at half speed at 3 in the morning, that's fine. That's why we record it. Those videos get used a lot in practice in the few days before exams. That's good. That's why they're there. Along similar lines, there's no textbook for this class. And I don't mean that in the sense of I didn't adopt a textbook for this class. I mean, as far as I know, there is no textbook that covers the set of material that we want to cover. I have a bunch of lecture notes for the algorithm stuff. I'm writing lecture notes for the stuff that used to be part of 373. Again, I'm writing that as a reference for you, but I know there are bugs. I will give you extra credit if you find them. Who was the question? That actually is an excellent idea. No, I think it might be a good idea to try to set something up next week, because this week is just chaos. But let me talk it over with the rest of the staff and see if we can set something up. I will tell you for reference what my own personal name for 173 is induction and some other stuff. Okay. It's all about induction. And so in that sense, there will be a review of 173 tomorrow. But there may be some other stuff like, set notation and, one-to-one and on-to. And we'll talk about solving recurrences when it comes time to talk about analyzing recursive algorithms. So, there'll be review of stuff at appropriate points in the semester. But if there's something specific you want more of, probably the best thing to do is to post on Piazza. These are the kinds of things that I think I might need help with. Any other questions? This room is small enough that, in principle, I should be able to see your hands when they go up. But like many other academics, I sometimes get caught up in my own words and stop paying attention to my audience. So if there's somebody next to you with their hands up, raise your hand and point to them. Right. I recommend doing this in every class you're ever in. Right. This is a trick that I learned from my wife, who teaches calculus over in the math department in rooms with 250 students. You get this big sea anemone going over here, and you can't miss it. All right. So first of all, there are some technical terms in the name of the class. So just to start out, let's see if we can figure out what the title of the course means. So one of these words is probably a little bit more familiar than the other. What's an algorithm? Yeah. Okay. Set of steps used to accomplish some task. I want to. This is close, but I want to tweak it a little bit, because one of the wonderful things that we learn when we deal with computers is that computers are stupid and they only do what you tell them. Language matters. Right, so I'm going to be really picky about, let's say set when the order doesn't matter, let's say sequence when it does. So it's a sequence of steps. And these steps are sort of, you have to say a few things about them. In principle, each step that happens in an algorithm is something you can do mechanically. And I don't actually mean that metaphorically. I'll say a bit more about this later. I mean this literally, as in you can build a mechanism, or rather, your friends over in mechanical engineering can build a mechanism out of gears and pulleys that can execute these steps. They're things that we know how to do, more generally, things that we know how to do because we learned how to do them in earlier classes. We all know how to add. So addition is a step that we can put into an algorithm. We all know how to compare two numbers. Or more importantly, we all believe that we can build a machine that can compare two numbers. And so comparing two numbers is a thing we can have as a basic step. Now, algorithms are old. This is one thing that a lot of even modern computer scientists don't recognize. This is a reproduction of the first page of a book written in the early 1300s called The Craft of Numbering, and it starts at the very top in, of course, absolutely clear medieval Latin. Here begins the book of algorithms. Now, people got very confused when they started translating this book into English. This is actually in Latin, it's actually a poem. People used to, books were not that common even in the 1300s, so people made up mnemonic devices So in fact, this medieval Latin poem that describes basic algorithms for doing arithmetic is written to precisely the same meter as I am the very model of a modern major gentleman. I haven't had it memorized yet, so I can't sing it to you. When it was first translated into English in the mid 1300s, early 1400s, this was the English translation. It was just sort of commentary on the first line. This is the Book of Algorithms, and it's describing a story about where the word algorithm comes from. So the reason is, well, so there was this king of India, and his name was Al Gore. And he made this thing, and so they called it, they called it algorithms. And so, but then he gives another theory. He says, algorithmus, as it was called, it comes from algos, which is Greek for the same as, art in Latin or craft in English, and rides, which is Greek for number. And so you take algos and ridos, and you add them together, and then you add the syllable mus, and then you take off the D and the E, just like numbers. Oh, of course. That's not actually where the word algorithm comes from. And the mistake in here is, well, there's one mistake in here, which is that algos, it is a Greek word, but it doesn't mean art or craft. And rides, or arithmos, is a Greek word. You know what arithmos means. It shows up in the word logarithm, it shows up in the word arithmetic. It means number, okay? Does anybody know what algos means? It shows up as a root in words like analgesic, aspirin, ibuprofen, nostalgia, homesickness, neuralgia, condition of nerve pain. Algos means pain. This, of course, is also not the correct definition. And I really have to wonder because, as silly as it sounds, 13th century English mathematicians were not idiots. They actually had to learn Greek. It might also actually be, ismos, which means, like Marxism, so algorithm means, painism. No, but in fact, it was named after what would now be called an Uzbekistani tradesman who popularized the art of doing calculations with what are now called Arabic numerals, after this guy whose name was Al-Khwarizmi, the Khwarizmian, because he came from the province of Khwarizmi. Algorithm, as it was sometimes called, was really the art of doing math with numbers or symbols. And that's what it meant for probably 500 years. It meant the arithmetic that you learned in school. The ways of manipulating strings of digits in well-defined ways in a series of mechanical steps to compute other strings of digits. And this actually, was popularized in Europe a couple of centuries later by a man named Leonardo of Pisa, whose dad was named Bonacci. So they called him son of Bonacci, Fibonacci. And so he wrote this treatise for tradesmen. It wasn't so much for the, scientists as such as they were at that time, but for people who actually needed to deal with numbers from day to day, people who had, barrels of wine that they needed to keep track of, or herds of sheep and so on, pots of money. And there was a real battle between two types of people doing trades. There were the algorists over here on the left who liked using these weird things that were imported from Arabia called numbers. And there were the abacists who liked doing their calculations with very small rocks, or as the word is in Latin, calculi. Calx for rock, ulus being the diminutive. So rather than, say, no, you have to do calculus. You have to, calculate. You have to move little small rocks around. And no. It's much better to do things with numbers. There were competitions. There were fights in the street. There was gang warfare. This is Chrome versus Firefox. This is I'm a Mac and I'm a PC. This is Emacs versus VI. Or if you prefer, this is Emacs versus VI. But it really doesn't make any difference, because in the end, if you abstract away what these people were doing, it was exactly the same. The algorithms at some abstract sense were actually isomorphic to each other. You had certain positions of the calculi, little rocks that corresponded to a 4 in the tens column and a 3 in the ones column. And you manipulated the rocks in more or less isomorphic ways to manipulating the symbols. So to give you a specific example of this, I want to show you the algorithm that was actually used for multiplication. Now, this is the algorithm in its modern form. Okay. This is for multiplying two numbers. Now, this algorithm is not the one that is taught in the United States and in most of Western Europe. It apparently was taught in Eastern Europe up until about something strange happened in 1989 that made Eastern Europe change. I don't actually know whether this is an algorithm that's taught in schools in Asia or not, or whether they also use, whether Asian school kids also use the lattice method that most Americans learn. This is called variously Russian peasant multiplication, or Egyptian multiplication, or duplation and mediation. Duplation means doubling, mediation means dividing by 2. This is the oldest algorithm for which we have historical recordings. It appears in the Rhind Papyrus, which was written in 1300 BC, and at the time claimed to be a transcription of a 900-year-old document that had been lost. So, this is at least a 4,500-year-old algorithm. It's been in continuous use since then. So the idea is I have these two numbers, x and y, and I want to compute their product. So I initialize some local variable prod, which is eventually going to be the output, assuming I spell it correctly. And then I have a loop. As long as the first factor x is positive, I do the following. If x is odd, then I add y to the product, and then I divide x by 2, rounding down, and then I add y to itself. Okay. So if you want to see this in action, I'm not going to do this by hand, but this is what would happen if you wanted to multiply 123 by 456. So you start at the first line by initializing the product to 0, and then you say, okay, x is positive, so x is odd, so I'm going to add y to the product, and then I'm going to divide x by 2 to get 61, and add y to itself to get 912. Now, the basic steps that are involved here are being able to add a number to itself or multiply a number by 2. That's not recursion. It's because you can just do it by addition. And dividing by 2 is something that, a separate skill that you have to practice that also has a separate algorithm attached to it. Okay, so 123 is odd, so I'm going to add x I'm going to add y to my product. Then I divide and double. 61 is odd, so I add y to my product. 30 is even, so I don't add y to my product, and so on. And eventually I get down to 1. And then after I get to 1, if I divide by 2 one more time, x becomes 0, and so the algorithm terminates. Okay. Now, it probably came to some surprise to the ancient Egyptians that it actually works just as well the other way. I can flip the factors, I get a completely different process, but somehow I still end up with exactly the same answer. Okay? This is also, so this is the algorithm that the people on the left used in the 1400s. This is the algorithm that the people on the right used in the 1400s. This is also the algorithm that computers used in the 1970s and 1980s when they didn't have a multiplication instruction, right? Except they weren't given the numbers as strings of decimal digits. They were given the numbers as bits. And there's an interesting way to actually see what's going on. There's this pattern of, well, it was odd, so I add, and it's even, so I don't. And I can imagine, writing down 0 every time it's even, and 1 every time something the factor is odd. And I get this nice little sequence of bits. What is that sequence of bits? Of? Well, remember, it's 456, it's x, right? So what I end up doing here is I'm literally looking at the bits in the binary representation of x. If I see a 0 bit, I don't do anything. If I see a 1 bit, I write down a copy of y, which has been helpfully shifted to the left by the right number of bits. So it's just the lattice multiplication algorithm that you all know in binary, invented by ancient Egyptians in 4500 BC. There's a similar division algorithm, which was also discovered by ancient Egyptians in 4000 BC, that's also described in the Rhine Papyrus, that involves explicitly figuring out which powers of 2 go in, expressing things as sums of powers of 2, which means there are 3,000-year-old clay tablets listing powers of 2 up to about 30. It's actually kind of cool. So, this really is the algorithm that up until people started doing things in hardware using all sorts of massive parallelism, this is really the algorithm that people used in practice up until fairly recently. As long as we're talking about this, what's the running time of this algorithm? Yes? Okay, so the log x, but what are you taking as the unit here? Log x what's? Well, one way you could say this is certainly this while loop is going to iterate log x times, right? Because every time I go through the loop, I divide x by 2, and a reasonable working definition of log is how many times you have to divide by 2 before the result is less than 1. Right? That is the definition of log base 2 rounded to an integer. Okay? But if you were implementing this by hand, you were in ancient Egypt. You were an actual, as they would call them in the 1960s, computer working, i.e. a human who computes, in ancient Egypt. Could you execute each of those lines in constant time? Suppose x is a 50-digit number. That takes you, it's going to take you twice as long to divide x by 2, roughly, than if x is a 25-digit number. What's the time per iteration? How long does it take to add two numbers? Sorry? Well, I've got two lines that are, actually I've got three lines that are interesting. I have to add something to the product, I have to divide x by 2, and I have to double y. Remember what I said about basic steps? An algorithm has to be down, it's eventually distilled down to very small, very basic steps that we can, in principle, implement mechanically by device where we turn a crank. Well, so one of the questions that we have to ask when we say how long does it take is as a function of what? And when the answer is almost always going to be the size of the input. How much stuff are we given? How much space on the papyrus or the clay tablet do we need to take up just to write down the numbers x and y? To make this really concrete, let me imagine that this is a cray and not an Egyptian scribe, and the numbers are given to you in binary. So how many bits do you need to write down x? Log x. 1 for each iteration of this algorithm, because binary. Okay? So I'm going to assume that n here is the number of input bits. And that immediately allows me to say the number of iterations is linear. And now how long, because each of these numbers is roughly most n bits long. Okay? Now how long does it take me to add two n-bit numbers? Linear time. Add the first 2 bits, maybe there's a carry, add the next 2 bits, maybe there's a carry, add the next 2 bits, maybe there's a carry. All you ECE folks have built this device, I think, out of actual gates. You do standard ripple carry thing. Each of these additions is going to take order n time. And how long does it take to divide a binary number by 2 and round down? Well, it depends on how you represent the binary numbers, but crudely, throw away the last bit, right? So, but it doesn't actually matter at this point whether that's constant or linear, because other things in the algorithm are already taking linear time. So the time per iteration is order n. So the overall running time is quadratic, n squared time. You could have also figured this out a different way. Remember I said this is just the standard lattice multiplication algorithm where, say 1, 2, 3 times 4, 5, 6. And I start multiplying 5, 1. Add 8, 8, 0, 5. Haha. Okay. I don't know where the mistake is. Oh, yes. There's a 6 here, not a 5. Okay. How many digits did I write down? If each of the first 2 numbers had n digits, how many digits do I write down between the 2 lines? There are n lines, and in each one, at most n plus 1 digits, so roughly n squared. And I spent constant time writing down each digit, so the running time is quadratic. In about 3 weeks, we will see that this is not the best you can do. It took about 6,000 years for people to realize this isn't the best you can do. If you have taken a signal processing class, you've already heard of fast Fourier transforms, which are named after their inventor, Carl Friedrich Gauss. There's a standard thing in ubiquitous in science called Stigler's law of eponymy. Nothing is named after its correct inventor. Fourier was about 100 years after Gauss. Unambiguously, Gauss used the fast Fourier transform to calculate the orbits of comets. But we're still going to call it the FFT, because no one will know what you're talking about if you call it the FGT. In any case, you can use fast Fourier transforms to do better than this. We won't get as far as fast Fourier transforms because there's not enough time to do everything important and interesting and beautiful in one class. But there are notes which you can read. We'll get close. We'll get to something faster. Okay? Now, what we just did is fairly indicative of what we normally do when we design and we analyze an algorithm, except we sort of skip the design phase. We let some poor guy who had to live in Egypt in 4000 BC do that for us. You have a description of the algorithm, which you'll notice is not written in any particular programming language. It's basically just written as an outline in English with some symbols that represent standard things one does with code. I could easily translate this into Python or a C++ or Emacs Lisp or Bafunge or whatever your programming language of choice is. And that's good. That's why we present it in this form. This is the form that I want you to present algorithms to me. You don't know what my favorite programming language is. It's not yours. I don't understand, well, I do, but pretend that I don't understand the intricacies of Python syntax. Pretend that I've never heard of objects, because I wish I never had. Give me something that a bright student in CS 225 can implement. Right? That's the level of detail and the level of specificity that I want. We spent a bit of time figuring out, what's going on. The one thing we didn't actually do is prove that the algorithm is correct. So let me do that in one quick line here. Well, it won't be one line because it never is. How do you prove that an algorithm like this is correct? And I'll give you a hint. To first order approximation, every time I ask the question, so how do we prove, the answer is induction. Okay? So how do we prove that this algorithm is correct? Thank you. Okay, so I'm going to write down a boilerplate induction problem, induction proof. Okay, so I claim that this algorithm actually works. Okay, so let x and y be arbitrary positive integers. And what do I want to induct on? Set it. X. Why x? Why don't I want to do induction on y? Yeah, well, the while condition, but there's another reason that's a bit more significant. X is getting smaller. X is the thing that eventually will go down to something small, so we can apply a base case argument. Y is actually getting bigger. We don't, generally when we want to think about recursion, we want to think about something getting simpler or smaller. In this case, the thing that's getting simpler when we recurse, i.e. iterate, is x. So we want to do induction on x. So I'm going to write down induction hypothesis. is assume the algorithm works when the first argument is smaller than x. Notice, I did not say when the first argument is x minus 1, because weak induction doesn't exist. Okay? Now there are two cases to worry about. Well, actually, let me just strengthen the thing that we're trying to prove. Okay, so there are two cases that I need to worry about. What are the two cases? Okay, if we want to go that way, there are three cases. X is 0. What happens when x is 0? Good, you all got it. Nothing happens when x is 0. If x is 0, then the product I return is 0, which is correct. It's 0 times y, whatever y is. Okay? All right. Second case. Suppose x is odd. Then what happens is I recursively call peasant multiplication with x over 2 and 2y, but then I add y to the product. Okay, I'm doing it up there as an accumulator. I'm going to imagine that it's actually written as a recursive algorithm and just do the recursive call. By the induction hypothesis, this is equal to x minus 1 over 2 times 2y plus y, which by a little bit of algebra is xy. And case 3, snappy red uniform, x is even. You again have the recursive call, which by the induction hypothesis is correct. And a little bit of algebra gives you that it's really x times y. Okay? Again, this is something that we like to do. It's a loop, but it's recursion. You design the algorithm as a loop because in practice, it's actually much more efficient and much easier to understand what the algorithm is doing when it's written iteratively. But always think recursively. Always, 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 always think recursively, right? So, you know, you want to translate your favorite, you know, imagine I'm doing my favorite Glengarry, Glen Ross quote, you know, ATR, always think recursively. Always be closing. Unfortunately, I don't have the necessary prop to do that right. Those of you who've actually seen Glengarry Glen Ross know exactly what I'm talking about. Those of you who haven't, get thee to Netflix. Okay, so what do we do with algorithms? We have a task that we want to perform. We design a sequence of elementary steps that we claim accomplishes that task. We need to prove almost always by induction that the set of steps that we've outlined actually accomplishes the task that we set out to accomplish. Now, there are in other classes, in other contexts, in particular out in the real world, where you have a different kind of thing that you think about called a heuristic. Okay, in this class, there's the working definition of a heuristic. Okay, the definition of a heuristic is the autofocus on the document camera. Oh, come on, you can do it. There it is. Right, okay. It's an algorithm that doesn't work, right? If we say it has to multiply two numbers, that means I don't care what two numbers you give me. It has to return the product. Not, well, for numbers that appear in practice, it gets reasonably close. No, it does it every single time, the end. The other thing that we do is we try to figure out what the running time of the algorithm is as a function of the size of the input. And again, what we're interested in is always the running time in the worst case. Out there in the real world, we're often, the worst case is often weird and strange and unusual, and it's never going to actually happen. And you don't actually care about it. But in this class, when I say we can multiply two numbers in n squared time, it means if Satan himself appears and gives me two n-digit numbers, I can multiply them using this algorithm in n squared time. By Satan himself, of course, I mean me. Okay? You should always imagine I am going to feed your algorithm input. I am devious. I will find little corner cases. I will make your algorithm screw up if I can. If you prefer to think of something more realistic than sort of theological metaphor, I have colleagues who work at AT&T who specifically work on hashing algorithms that are used in the internet backbone. Now, the nice thing about hashing algorithms is they're really, really, really fast, provided that you satisfy a bunch of theoretical assumptions that no one ever talks about. The horrible thing about the internet backbone is that there are billions of executions of that hash function every day on every internet router. And moreover, there are people millions of times a day deliberately trying to force collisions, trying to do timing attacks on the backbone routers, trying to figure out what that hash function is so that they can bring the internet to its knees. It's not clear whether these people are acting intentionally or whether they're just stupid, but it is an actual fact that without very, very strongly guaranteed hashing algorithms, where you can say very clear things about collision probabilities and running times under extraordinarily adversarial circumstances, the internet will end, right? This is a real thing that, if it fails, costs people's lives, right, that we use every day, right? If the algorithm has a corner case that will go wrong, eventually the airplane will crash. Or, as actually happened, the satellite will crash into Mars. That was because one group of software engineers was using imperial units when everyone else was using metric. And so they said, oh, Mars is 100 miles away. Let's go. Actually, no, it's 100 kilometers away. Real story. So it has to work all the time. It has to be efficient all the time. Everything worst, 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 worst case. We are undying pessimists in this class. Okay? And now the flip side of this, the other half of the class, is, well, there are things we don't know. Right? There are things that, whoa. All right, somebody needs to fix the, let's try autofocus again. There we go, okay. All right, so one of the things about algorithms that we sort of take as a minimal condition of being an algorithm is they stop. You run the code, and eventually it gives you an answer. Or eventually it stops running. Nobody knows whether this is an algorithm, because nobody knows whether this bit of code, I might as well call it an algorithm, but nobody knows whether this halts for all n. Now, we do know that this algorithm halts for every n less than about, I think it's like 10 to the 120, which is all n that would ever arise in practice, but that word in practice is outlawed here. And 2 to the 120, small potatoes, right? When I say all n, I mean all n. Nobody knows whether this halts. This is the famous hailstone sequence, or the Collatz sequence. If it's even, divide it by 2. If it's odd, triple it and add 1. I'll let you fiddle with this on your own, but if you want to torture yourself, start with 27. You'll get up to at least 4-digit numbers before you come back down, but eventually you'll get back down to 1. And every number we've ever tried has gone back down to 1. But we don't know whether it always goes back down to 1. And there's actually, some quasi-half-baked reason to believe that not only do we not know whether this algorithm halts, we cannot know whether this algorithm halts. Certainly there are things where we know that there are theorems that are true within any particular logical system that we can't prove. This is Gödel's incompleteness theorem. This is another lovely little piece of code. It's 3 lines long. The last line is a comment. This is a proof of that there is no way to write a Python program, say, that takes as input a Python program. So actually, to keep it simple, let's say there's no such thing as a C program that takes a Python program P as input and returns true if P always halts, no matter what its input is, and returns false if it's possible to make P loop forever. Okay, this is the so-called halting problem. I give you a piece of code, and instead of feeding it to a compiler or an interpreter, I'm going to feed it to this other program that says, yes, no matter what you run this program on as input, the program will eventually halt and return an answer. Or, hey, no, this is dangerous. There's a way to make this thing fall into an infinite loop. Okay, suppose a program like this exists. Well, let's call it always halts. Well, if I can write it in C, then I can write it in Python. And so here is a piece of Python code called headexplode. Now, what it does is if the Python program that it gets as input always halts, then headexplode loops forever. If the Python program P that I'm given as input might loop forever, headexplode halts. Okay, anyone want to guess what I'm about to do? Feed it to itself. Okay. What does that do? This is perfectly legal code. This is a Python program. This is a piece of text which, when run through the Python interpreter, becomes a Python program. Right? This is one of the ways that we figure out things that can't be done is you have this sort of self-reflection. Whenever we try to look at ourselves in the mirror, we can't see the back of our head. It's exactly the same sort of thing. When somebody says, I'm a liar, are they telling the truth or not? The first occurrence of that, I believe, is that I know of is from the 11th century BC. Psalms 116:11. I said in my haste, all men are liars. Anyway, this program takes a program as input and tries to figure out whether it always halts or not. All right, so let's see. Suppose headexplode on input headexplode halts. But then always halts will return true and it'll loop forever. So if it halts, then it doesn't halt. Okay, great. So let's suppose headexplode gets into an infinite loop. Well, in that case, always halts will return false, and then headexplode will immediately terminate. So if it loops forever, then it halts. But if it halts, then it loops forever. If I'm lying, then I'm telling the truth. If I'm telling the truth, then I'm lying. So I've painted myself into a logical corner. And the way that I did this is by assuming that something exists that doesn't. Namely, this program called always halts. I assumed that there was a program that can tell me whether a program halts or not. And from that assumption, I derived that this program halts if and only if it doesn't. Okay, so I must have started with an incorrect conclusion. So this is an example of a problem for which there is no algorithm. Okay? Now, this version of this proof is essentially exactly the same as the argument used by a second-year PhD student of Alonzo Church named Alan Turing. Turing was amazing. This one paper, right, this one 1936 paper sort of established that, you know, this is what computing is in an abstract sense. Both in the mathematical sense of this is the proper abstraction of what it means to do mechanical computation, the Turing machine. So you have this infinite sequence of tapes. You have a box that can exist in a finite number of states, some number of states, 123 states. And each of the symbols on the tape can be one of 100 things. And the only thing the machine can do is look at a particular cell on the tape. Based on its internal state in that symbol, it can erase it and write a different symbol, and then move one step to the left, one step to the right, and change what state you're in. Turing actually, in his paper, said this is really an abstraction of human beings doing calculation with paper and pencil. The state is do I have my linear algebra book open, or do I have my factoring polynomials book open, or do I have my arithmetic book open that Fibonacci wrote in the 1300s? Right? And where I am in my calculation is which piece of paper am I looking at? Eventually, oh, okay, I'm done with this calculation. I copy this number into line 7 of schedule 1040A. Then I go over to this piece of paper and start something, you know, that going back and forth between various pieces of paper, solving different tasks which you can't keep track of in your head. You have to write down where you are. That's ultimately what a Turing machine is based on. Gödel proved the Gödel's incompleteness theorem, which says you can't prove everything that's true. And this was, you know, in 1931. And, you know, this immediately implies, if you think of proving things as a mechanical process, that there are problems you can't solve. But Gödel said, no, this is not really the right answer. This is not what mechanical computation means. Then Church came along in 35, 36, and invented the lambda calculus, and was actually the first to prove that there are undecidable problems by basically inventing Lisp. And Gödel said, well, yeah, that's pretty good, but it's better. But still, something's missing. And then Turing came along and Gödel said, yes, that's it. Now we understand. This is what it means to actually compute hardcore logicians. On the other hand, Turing's colleague on this side of the Atlantic Ocean, John von Neumann, took a different attitude to Turing's results. He said, oh, you can actually imagine storing a set of instructions over here in this box, or you can think of storing the set of instructions down here in the tape. And so this was John von Neumann's inspiration for the stored program model. This is why Turing is why we have a CPU over here and a memory over there. This is the state machine, this is the tape. Right? Von Neumann invented this thing called random access memory that actually made things work quickly, but it's directly based on the work of Turing. So for, you know, historical importance reasons, we'll have to talk about Turing machines. But before we can talk about Turing machines, and before we can talk about algorithms, we have to talk about simpler things. So backing up in terms of the levels of abstraction, first, before we can talk about Turing machines, we have, with both finite state and memory, we have to talk about just what you can do with finite state. You have no memory at all, right? So this is a finite state machine. Unfortunately, I didn't print this out in color. For those of you who've never played Candyland, or don't, like me, have a 4-year-old daughter, Candyland is a game where you have a little token that you put down on one of these little colored squares, and you draw a card, and on that card, it has a little square in one color of one of these colors, or perhaps two. And if you get the red square, you move your token to the next red square on the path to the end. If you get a card with 2 red squares, you move to the first and then the second red square. So the state of the game is, where is my token? The input to the machine is, what's the next card? And based on what cards I get, I move from one state to another. I don't have any real memory. I can't write down or record arbitrary numbers by placing a token on a Candyland board. There are only, 100 different squares on this board. There's no way to record the number 317. I can't remember arbitrarily large things. I only have one piece of information. Where is my token? And I can only do one kind of thing to it. I get a red square, I move the token from one state to another. Okay. Now, I also have an older child who likes to play with slightly more complicated finite state machines. This is a finite state machine that has 19 quintillion states, roughly. The input to the state is, how is the cube scrambled? What colors are on each of the little 9 parts of each face? And the input is, rotate the left face 90 degrees, rotate the top face 90 degrees, rotate the bottom face 90 degrees backwards. And based on this sequence of inputs, which come from some small finite alphabet, this machine moves from one state to another. And if I execute the right sequence of inputs, I'll get to a particular state that I like, which is all the faces are solid. At which point I say, I'm solved. Yes, you correctly solved the cube. So you can think of this as a decision problem. If I give you a cube scrambled and I say left, right, up, down, top, front, top, left, right, top, down, is the cube solved? This is a problem. There's an algorithm to solve it. I don't have to remember very much to execute this algorithm. I just have to have a cube that I can scramble. I can't record numbers like 2 to the 100 on a cube, so I don't have unbounded memory. Finite number of states. Okay, so we're going to also be talking about finite state machines and things that are related, like regular expressions, context-free grammars, and even simpler things starting on Thursday about, how do we think about strings? How do we do math? And so that sort of leads us backwards to where we start on Thursday. Are there any questions? If there is anyone here who is not actually registered for the class, please come up and talk to me before you leave. Thanks.